Hey, hi
Hello.
everyone. We are finished the fourth day for the summer school. President
Oof.
to the next lab, the number two. I hope you love this idea because we discussed with Jorge. We did a job try to make different things, focus mostly on how we can work with translation. What is the new things about the backend, the noise model, how can you do it, and the error mitigation. So we really, I love this idea, and we hope you can share the same thought with us. So let me introduce myself. First of all, I'm Alberto Maldonado. I'm a quantum computational scientist in IBM Quantum, and we'll try to mention of these collaboratory different things, but we share right now with Jorge, with amazing intern in Avian Quantum, who practically did this job. He do it. He put all in her hands. So practically, I need to recognize all this work is for Jorge. He just started the idea, and we do a small thing, but he do a big challenge.
Thank
So
you.
yeah, all the credits is for Jorge right now. So Jorge, I will share you the word to make a presentation for all the biggest work we are doing during this internship. So yeah, go ahead, Jorge.
Yeah, thank you, Alberto. So my name is Jorge Martinez de Lejarta, and I work with the EMEA Workforce and Quantum Education team here in the Zurich lab. And it's my pleasure today to host you in this lab to walkthrough, which is, as you have probably seen, the title of the lab is Cutting Through the Noise. So I think we can get started. I will share my screen and I will guide you through the different things in the lab. Okay. I guess that you can see my screen, right? Alberto, can you confirm? It's all good?
Yeah, all good.
Okay, perfect. So yeah, welcome everyone. Essentially in this lab, we are going to dive into the world of quantum noise and in particular see the different techniques that allow us to navigate the challenges of quantum noise in order to obtain the good results with the current quantum computers. We will address a small size max-cut problem and we'll guide you through the different steps that one should follow to reduce the quantum noise in order to obtain good results with a quantum computer. And we'll also explore different transpilation and error mitigation techniques to minimize the errors and ensure that the results are still good despite the noise. And finally, there is also a bonus exercise about executing all these techniques that you will learn on the real hardware. So let's go through it. This is the table of contents, and these are the requirements that you should not have any problem like with these libraries. Everything should be installed already. And yeah, before digging in, I would like to mention that the spirit of this lab is to walk you through the process of tackling a real world, like in general, real world problems by using the right explanations and error mitigation techniques to maximize the performance on the IBM quantum hardware. So before starting, let's start with a simple question like, what is quantum noise? That might be familiar to some of you, but maybe not so much to others. So noise is a central topic in quantum computing. And essentially, we usually refer to this term as any unwanted transformation that disturbs the expected outcome of the measurement of a quantum state. And that includes like a wide range of effects that we can usually group in two categories. The first ones are the coherent errors, and they are caused by small and consistent mistakes in how the quantum operations, the quantum gates, are applied. So, for example, you can consider a Hadamard gate that can be slightly miscalibrated, and that means that it will not create the perfect superposition state. On the other hand, we have the incoherent errors, and the origin of those it's more like naturally quantum because it comes from the interaction of the quantum system with the environment. So, for an example, could be the relaxation time T1 that describes how quickly a qubit in excited state 1 can decay to the ground state 0 over time. Okay, and then the next point will be the different sources of noise that we have. So there are different metrics that we can use to evaluate how good or how noise resilient a quantum computer is. And among these, we can distinguish a few. So we can distinguish the relaxation time, the phasing time, and also the single qubit, two qubit gates fidelities, and also the readout errors. And we are going to see all of this in detail actually in the first exercise that you will need to complete. So essentially, this first exercise is about finding the qubits for a particular backend that has the best of each one of these metrics. So that means that we need to find the qubits that have the best relaxation time, best defacing time, smallest readout error, smallest single and two-qubit gate errors. And also, we need to find the qubits that has this metric and also the metric itself, the value. So here we'll show you how we can access these properties of a particular backend. We are working in this case with the IBM Quantum uh, computer, IBM Brisbane. And yeah, the first exercise is about completing this function that find the best metrics. And these are the different things that you need to complete. And if everything works well, you will see a message like this, as you are already familiar probably from lab 1 and lab 0. Then the actual problem that we are going to address in this lab is a max-cut problem that might be familiar to some of you. It's essentially a graph problem that is in the category of NP-hard, which means that there are no any algorithm that can solve it in polynomial time. And just like a brief description on what this is. Essentially, we can view this problem as a problem of finding the maximum cut in a graph that divides the graph into two nodes in a way that this cut traverses the maximum number of edges. As we can see here, that this traverses 5 different edges. And then we can define an actual graph, an actual problem that we will need to solve. In this case, this is the graph that we considered for this exercise. And then the next step would be to map the graph into a quantum computer. This is actually, in many cases, this is one of the most difficult parts when you are designing a quantum algorithm. So you need to map your classical problem into something that can be understood by a quantum computer. And this is, in many cases, not so easy. So in particular here, what we are going to do is we are going to work with one of the favorite mathematical objects of quantum computers, which are the Hamiltonians. And in particular, we are going to use the Ising model, Hamiltonian. You have here all the theory and the useful links in case that this is you are not very familiar with this. And yeah, the second exercise is about that. So you will need to convert the graph object that we just created into an Ising Hamiltonian. And then what we are going to do is later is to execute the QAOA algorithm, the quantum approximate optimization algorithm, that essentially will solve this problem using this Ising Hamiltonian. You don't need to code this and you don't need to know much about this algorithm, but if you want to learn more, there are very useful links here that you can explore. And yeah, all of this part is coded for you. So you don't need to do anything because the focus on this lab is about transpilation. But you will see that the results will look like this. And these are the specific cuts that, that, that are the solution of our problem. Okay, and with that, we can jump to the next part, which is about working with noisy quantum simulators. So these simulators are very useful tools that aim to mimic the behavior and noise of a real quantum processor. So they allow us to test and evaluate how good our quantum algorithms are. So sorry, how our quantum algorithms would perform on actual quantum hardware without consuming the valuable resources of actually executing it on a quantum computer. So this is why these noisy simulators are a very powerful tool. So now we'll need to choose the backend. And in principle, if you are using the free plan, you should get these three backends. And, and then we are actually going to use the simulators that take the noise model from the backend, as you can see here in this line. And once we have done that, we can jump to the third exercise, which is about error counting. So your goal in this exercise is to estimate the total error that the quantum circuit is going to accumulate. So we need to actually go through all the circuit instructions in the quantum circuit and accumulate the error that every single operation is introducing. So you will need to count from the single qubit and two qubit gates errors, and also for the readout errors that are related to the error that we have when we measure a particular qubit. And yeah, this is the function that you need to fill in this exercise. And here you have some pre-coded parts so that will guide you and will help you to complete this function. So you don't need to do it from scratch. It has like some pre-coded part, and you just need to fill some of the gaps here using the helpers that you have here in the comments. Okay, and then you can execute these lines, and you will see uh, something like this, and you can also visualize the results. You will get something like that. Yeah, also here I would like to say a disclaimer that all the results that you see might vary from the ones that you will obtain when you execute this on your own, because this is actually taking the data from the real quantum computers, and this calibration of the quantum computers changes with the time. So it changes every few hours. So the results that you will see might be different than those that you are seeing here. So don't worry. The important part is that the logic of everything that you do is correct. Okay, and now you can execute the QA algorithm on the different backends, and you will see like the results that will look like this. And then you can also use NEAT to estimate the errors. That I will not go into detail now, but you can also use this and take a look of what this means. Okay. Then the fourth part is about using the transpiler. So the transpiler is one of the most important and useful tools in the context of executing quantum circuits on the real quantum hardware, because it serves as the bridge between the abstract quantum circuit that we design to solve a problem and the actual quantum circuit that is going to be physically implemented in the real hardware. So this is why Transpiler is so important, because actually if you master all the techniques of transpilation, you will be able to get the most out of the quantum computers and get the best possible results. So with that, this first part is about we are going to create a function to minimize the two-qubit gates errors, because actually in the majority of the quantum circuits, the most of the errors are coming from the two-qubit gates. So that's why it's in many cases one of the most important part that we should try to minimize. So we are defining this function that will be useful later, and we are transpiling our circuit using the IBM Brisbane backend. And then, yeah, you will see that doing this naive or like a default transpilation, we will get like some results like this that might vary from when you execute it. And then we jump to the next part, which is about finding the optimal layout. So usually we refer to this thing of finding a like optimal layout to the process in which we try to map the logical qubits in which we have designed our circuit to the physical qubits where our circuit is going to be executed on the real quantum computer. And it's important that this mapping is efficient and is done in the proper way. So usually, if we like to do the perfect mapping, that will require to take into account many different things. But here we are simplifying this problem, and we are just selecting the qubits that satisfy the same connectivity that the default transpilation that is done above. And also, we are trying to get the qubits that have the smallest two-qubit gate error rates. So yeah, this is what this part is about. We can also create a graph that contains the information of our backend. Here the nodes are the qubits, and the edges are the different connections between our qubits. And then we can also create a list, this logical pair list that contains the different two-qubit gates that we have in our circuit. Okay, and with that, we have enough information to introduce the fourth exercise, which is about finding all the good qubit layouts. So this exercise, you are asked to find all the possible qubit layouts that have a smaller two-qubit gate accumulated error than the transpilation that is presented above, and at the same time that present the same connectivity as the transpilation done above. So these two things are accounted in these variables, the accumulated two-qubit error and the logical pair list. So using this, you must be able to find all the possible qubit layouts that have a smaller error. So You can try this on your own. There are like different ways, but here we have recorded a particular approach to do that, which is this function. And actually here, what you need to fill is how we are getting the weights out of the different graph if the neighbors that we are exploring are directed neighbors, and how we are getting the weight if the neighbors are undirected neighbors. So this is also something that you will need to explore in the different libraries and the different functions that are here, but it should not be too difficult. And then, of course, you need to check that the weights that this path that you are looking for are still smaller than the threshold. So you need to make sure that we are beating the threshold that was in the previous default transpilation. Okay, and with that, actually, the goal of this part is to show you how tedious is in general, like to do like a good transpilation to make sure that you are performing like the perfect or the best possible layout. And but luckily for us, we can rely on the pass manager class that we have in Qiskit that will do that for us. So we can, this is what we are going to see in the fifth exercise. So we are going to find the best mapping, but now in an automated way that is much easier. So we are going to use the saver layout method to identify which one is the layout that has the smallest two-qubit gate accumulated error. And to do so, since Saber is an stochastic method, that means that that it has some initialization that is random. So we can set the seed for this method with different values to see which with which with we will see which initialization works better for our method. So this is what we are going to do now. So you will need to run to perform a sweep over different values of the seed from 0 to 500, and you will need to save the circuit that has the smallest error. And these are the tasks that you need uh, to fill and to complete for this fifth exercise. And then later you can also execute how are the results with the like the default transpilation and the optimized transpilation, and you will see that in general with the optimized transpilation the results look much better. Okay, cool. And with that, we are coming to the last part of the lab, which is about error mitigation. So error mitigation consists of a set of very intelligent techniques that are designed to reduce the impact of noise without requiring complex, complex error correction codes or additional qubits. And there are many error mitigation techniques that could be useful, but in this lab, we are going to focus on the zero noise extrapolation technique. You can think of this technique as something that is composed of two parts. In the first part, we will need to amplify the noise. We want to have even more noise than the one that we have in the initial circuit. And the reason to do that is that if we just like create like different values, different amplifications of the noise, later we can do an extrapolation to the case where there is actually no noise. So we can do an extrapolation to the zero noise limit. Okay. And actually, there are different ways in which we can perform this noise amplification. We can do the global folding. In the global folding, we are actually we are just like describing the whole circuit with a unitary, and then we are folding this unitary. What does that mean? That means that we can actually uh, substitute the unitary that we are using to create our circuit by something that looks like U dagger, and U. And we can do that because U and U dagger will cancel out because this operator is unitary. So this is what means folding in this context, and we can do that for different scales. So we can apply this UU dagger like a number of times, the number of times that we want, and we will have, of course, more noise the more number of times that we apply that. Okay, so this is what global folding is about, and this is what you will need to do in the first part of the sixth exercise. So here you will need to fill this function, and you can use this these functionalities of Qiskit to perform this task. And then the other method is local folding. So local folding is doing something very similar, but instead of folding the full circuit, we will fold every instruction in the quantum circuit. So we can apply like the same logic, but for every gate in the quantum circuit. And this is what you are asked to do in the 6B exercise. So you will need to perform the circuit folding for every instruction, but also make sure that you don't fold the measurement gates because they are not unitary and you will get an error. Okay, and that's everything regarding the graded exercise, but there are still more in this lab that you can explore. So you can also run the next cells to see how is the extrapolation and if we are actually doing better using this technique. And if you run the cells, you will see that we are actually obtaining a smallest value of the expectation value of the ground energy of the Hamiltonian, and that means that we are getting a better result. So you can see that for these extrapolations, we are reducing the value that we would get if we don't use this technique. So that is definitely a good sign. Okay, and just to finish this walkthrough, I would uh, I would first like to tell you that there are some takeaways that I hope that you remember after completing this, and is that when you want to execute a quantum algorithm on quantum hardware, you should follow these steps. So first, you'll need to choose the right hardware that is well suited for your circuit. Then you'll need to use the transpiler to select best possible layout and minimize the number of 2-qubit gates or other metrics that you might consider. And also, it's important that you apply the error mitigation and suppression techniques to further reduce the impact of noise and improve the performance. And actually, there is still something else. There is a bonus challenge, as it was also the case in the previous exercise, which is also about executing things on real hardware. In this bonus challenge, we are actually scaling the problem. We are making it even more complicated. We are doing it with 7 qubits in this case. And then the steps to follow are very similar. So you will need to choose the right backend, then you will need to optimize the layout and minimize the error. And then you can first execute it on simulator and see how are the results. You should obtain something like this, more or less. And then you can check if your results are correct or not. And then we get to the actual fun part. We can run all of this on hardware, but I would like to say a disclaimer that that could take between 2 or 3 minutes in the free plan. So make sure that you have this time, otherwise you will not get any results. But I think that if you have the time, it's something very useful to do because then you can actually play around with different error mitigation and suppression techniques that will make you learn a lot about this and in which situations it can be useful. So here you have some examples without them, and then here you have some examples with the different error mitigation techniques that you can, actually, of course, tune and do as you want. And then here you have the same for the sampler. You can also apply error suppression techniques with the sampler and see if you are actually getting better results or not. And I think that could be everything from my side. Now I would be very happy to take your questions if there are.
Great. Yeah, it looks like we have about 3 questions. I don't know if
Okay. Yes.
I,
I can see the first one is the Tanner tour, no? Or what is the first one? Let me go up.
Yeah, the first one is when you run the simulation,
Yes.
is it running local or on the cloud? It's on local.
So sorry, I didn't hear you. And when you run the simulator, is it run local or okay? Yeah, when you run the simulator, is everything is running local. Everything is running on your machine. So that also has advantages because you don't need to wait for the associated queues when you run like something on cloud devices.
great.
Then
Another question.
yes.
I can pop
Okay,
it up
perfect.
on this.
Okay. How can one estimate the polarizing errors in a given quantum hardware? For example, to estimate the polarizing errors in the pure gas, one could average. I cannot see the full question, but essentially, there are like some functions in the backend. You can access the properties of the backend, and you can access like the error that every gate is like in principle accumulating for every particular qubit. So you can, there is an example like before the first exercise, there is an example of how you can get this information from the backend. And it works for single qubit gates, for two qubit gates, and like any metric that you want to measure, you can access it. And there is like a specific cell that is about that, so you can see an example. Uh, okay, the noise from the backend, yes, the noise from the backend is every few hours. Well, uh, it's not exactly that the noise changes. The thing is that the devices are calibrated every few hours, and so that means that they need to perform like different calibrations on the different qubits, because like not every time the gates are going to be calibrated in the same way, because the devices are not static, they are dynamic. So you need to take that into account and to make the calibrations differently. That means that sometimes the qubit 24 could be like super good qubit, but then like maybe 1 month later, it's not as well calibrated as it used to be, and the 24th qubit is actually the worst. So that's why it's also like kind of tricky to work with quantum hardware, because you need to be like always taking that into account, and keep updating your different techniques, and exploring all of that. Are there any other questions? Does Saber require dynamic circuits? No, you can just run like any any circuit, and you can transpile it uh, using the pass manager. Uh, 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 we have 10 minutes. I'm reading this. We have 10 minutes for the hardware. So how do you recommend we use them wisely? Like in which labs? I think that, well, first of all, that depends on you. Like if you are interested like in transpilation error mitigation techniques, yes, then please use it here in the second in the lab too. But if there are other topics that are most of your interest, maybe you can try to save some of it. But in general, I think that at least you can run. I mean, we have done it in a way that you can run in principle all of the bonus challenges once. So you can try to run everything once in this lab. And if you are really interested and want to learn more about this, then you can try to play around with the parameters and see if you get better results when you change the error mitigation techniques. That would be my advice. Um, when we access the noise parameters of real quantum hardware, will it cost time or execution limit on real hardware? No. You are just like getting the information from the hardware, but you are not submitting any job. So that means that this is not counting as execution time. So you can always access the information of the quantum hardware, but until you don't submit any job, you will not lose any time on the cloud. Okay. Uh, okay, let's see here. Is the noise of the qubit, or is the noise in the qubit, it depends on the number of times it's used? No, not necessarily. Like the noise of the qubits can depend like on many things. But you could have like for example that some gates are not so well calibrated for a particular qubit, and that doesn't mean that it works worse than than the than it doesn't work worse because you have used it like many times.
Great. And if you want to choose one more, we might have time for one more question. If not, we can close out for the day.
Okay, maybe this is okay. Yeah, maybe the second one is important from a like a technical like purposes. So actually, there are. So he's asking if can clarify if the mandatory part of this lab will use cloud minutes. So the answer is no. You can run everything that is in the notebook until the bonus challenge, and it will not use any of your cloud minutes. So you can just save that if you want. You don't need to use the cloud minutes to actually get like all the exercise answer, and to get potentially at the end of the summer school your batch. So don't worry about that.
Great. Well, thank you both for coming and teaching today's lab. I really appreciate it. For everyone else, they will be on Discord.
Perfect.
And we will open that part of Discord up. Thank you so much for everyone tuning in.
Okay. Thank you. Have a good one.
Thank you, everyone.